Hey everybody, this is Brian, and doing a video here, kind of a follow-up on the video I posted a few days ago on the 4-wire resistance and the Seebeck effect. In this video, we'll go over some of that same ground and go a little bit deeper into it, but the early part of this is going to really cover the fact that there's more than one way to skin a cat here, and as far as 4-wire resistance is concerned, generally speaking, only benchtop digital multimeters have 4-wire resistance as a feature built into them. And regular handheld multimeters do not. But you don't absolutely need a precision high-dollar bench multimeter to do 4-wire resistance. And I'll show you 3 different ways you can do 4-wire resistance measurements. The first one is obviously the use of an actual multimeter that has 4-wire resistance built into it. And in my case, I have a Rigol DM3058E benchtop multimeter, which is basically the bottom end of the market for benchtop multimeters. But it does have 4-wire resistance measurement in it. And the idea behind 4-wire resistance measurement is you have a multimeter that provides one loop using 2 leads to provide current to the device under test. And then with a known current flowing through the resistance, the other set of leads is just there to measure the voltage drop across it. And doing it that way, you don't run the voltage and current measurement through the same leads as you would do with a 2-wire resistance measurement, basic to most multimeters, including handheld multimeters. So, and you can see how I've kind of sketched this here. You have the device under test, be it a wire or resistor or whatever it is, and you connect up to it at 2 points on it, and ideally you would have the current and voltage source at each end connect at a single point on the wire or component. And that's not always practical. You have leads that are of sort of finite size that don't kind of go on top of one another. So there's a limitation on what you can do there, but by and large you would prefer to have the contact at a single point to provide both the voltage, the current and then the voltage readback. In the case of my benchtop multimeter, and probably a good many of the benchtop multimeters, the current source is a precise 1 milliamp, accurate to probably 3 or 4 decimal places, possibly more. But bottom line, an accurate 1 milliamp current source. So as that's flowing through the circuit, presuming you have a complete circuit, then whatever the resistance is, the current that's flowing through it is going to produce a voltage drop, and the second set of leads are then able to measure that voltage drop, and it's just a simple Ohm's law, V equals I times R. So if you know what I is, you can calculate R by dividing V by I. Very simple. And that's what the meter does internally, of course. But again, you do not necessarily have to have a 4-wire resistance measurement capable instrument to do 4-wire resistance testing. And the second method, and I'll skip over here, uses basically 2 multimeters, and you need a current source. So one multimeter is only used to measure voltage, and its leads go to the test points just as before. The other multimeter is only used to monitor the current. Presuming you're using a bench power supply, or you could use a battery, or there's any number of things you could use. The bottom line is you need to know what the current is in order to be able to calculate via the voltage drop what the resistance is. So in this method, assume for argument's sake you're putting 15 milliamps through the circuit, right? And you measure 15 millivolts as your voltage drop. Well, then you have a 1 ohm resistance. And it just works out. Again, Ohm's law applies in the same fashion. And again, the idea here is you have the leads tying as close to one another at the test points as possible. The power supply, in this case, does not have to be an ultra-precise power supply where you specify the current precisely from it, although that's an advantage, obviously. What is an advantage, or perhaps more important, is that the current isn't bouncing all around, because ultimately you need to be able to record the voltage and current at the same instant, or very nearly so. And if it's bouncing around, that could make that difficult. The more stable the current is, the better. So that's the second method, and there are some advantages in doing it this way, and I'll talk about that in a bit. The third method uses just one digital multimeter, and again, in this case, just to measure the voltage. And the other one uses, the other part is a precision power supply, and the more precise the better, because you need to be able to accurately set the current in order to be able to, via the voltage drop, calculate the resistance. So that's the three basic methods, and your lead hookup to your device under test is basically the same in all three cases. And of the three, the one that generally is preferred is the first one, using an instrument that has the 4-wire resistance capabilities built into it. However, there is a certain advantage to using the second method. And I got that backwards. Let's bring this back. This is the one I'm talking about. There is an advantage to using this method because you can vary the current. Again, with a 1 milliamp current source, as typical with a bench power supply, a bench multimeter, if you're trying to measure very low resistances, let's say 30 milliohms, with a resistance that small and sourcing 1 milliamp, the voltage readback is just 30 microvolts. So, a lot of multimeters, even bench multimeters, certainly if they're only 5.5 digit as mine is, that's getting down into the sort of the limits of its resolution and binning. So if you can multiply the current by a factor of 10 or 100 or even more, then you increase your reading resolution accordingly. For example, if instead of sourcing 1 milliamp, you sourced 100 milliamps, now if you're measuring that 30 milliohms resistance, instead of a readback in the order of 30 microvolts, you're in the order of 3 millivolts, a much easier signal to read and to be able to read more accurately. So there are some advantages to this method, and there are some additional advantages which we'll talk about in a little bit. So that's the probably of the three, the one that gives you the most options. The system with the 4 wires built into it is the most convenient, obviously, because you don't need any other instruments. And the limitation, the main limitation of the third method, using just one multimeter and a precision power supply, is that the limits of how accurately you can set the current in your power supply, and then how accurately you can know what that current is. Not just how accurately it's set, but how accurately you can read what the setting is and what the actual current is. So of the three, this is the least accurate in most cases, although the accuracy, as with the second method, tends to improve as you increase the current. Because whatever errors you have, nominally an instrument capable of, say, 1 milliamp resolution, it's going to have nominally about a milliamp or so of error, which when you're trying to set a set point in the 1 milliamp area means that you could be off by basically 100%, which isn't good. But if you're up around 100 milliamps, now your error is perhaps 1%. So, like the second method, a higher current, if your circuit tolerates that, is an advantage. There is a negative aspect of running with a higher current, and that is that as you run with higher current, and the higher the current you run, then you begin to introduce, or you can begin to introduce, heating effects in your device. And usually with resistive elements, as you heat it, the resistance changes, usually higher. So, and the formula that covers that, and we're looking at, for example, a piece of copper wire, and I have the alpha for copper, that's the typical value for that, although various alloys of it are probably somewhat different. But the bottom line is, as you raise the temperature, the resistance increases. There are items with negative temperature coefficients, but for the most part, most resistive elements are positive temperature coefficients, so as the temperature raises, the resistance rises. Okay, so let's go back here. Okay, so starting back on the 4-wire resistance measurement tool, we have the setup here. Basically, I have a wire under test. It's basically about a 750 millimeter length of approximately 22 gauge solid copper wire, and I have it connected to the negative end of a current source and voltmeter, and negative end of the current, positive end and current. Positive end of the current source and voltmeter at the other end. All of that going to the 4-wire inputs of my multimeter, and I'll show you the meter in a minute. In 2-wire mode, and what makes 2-wire mode a challenge and where the errors come into play, is that the current is sent through the same wires as the voltage sense. So you measure the voltage drop not only of the device under test, but also the leads going to and from the meter. And perhaps even more insidious is the variable resistance of the contact between the meter leads and the device under test. This is very easy to test, and you can verify this for yourself. Take a multimeter, put it in ohms mode, and short the leads like that. Short the tips of the leads like that. And you will get, 1 or 2 ohms, maybe a 0.2 ohm, maybe 0.1 ohm. And, oh yeah, you can do the relative, so you zero them out so you cancel out the leads. But then watch the resistance. Just keep watching it as you're holding the tips shorted. You'll see the resistance continuing to bounce. Nominally 1 or 2 or 3 tenths. But if you're measuring a resistance that's sub-ohm or low ohmage, then a 1 or 2 or 3 ohm dithering because of contact resistance and variations in contact resistance completely swamps the signal. So you don't know what you're getting. And that's the problem with a traditional 2-wire resistance measurement. In addition to the additional resistance of the leads, which you can cancel out with zeroing or relative mode, you still have the dithering of contact resistance with the meter leads themselves, the contact between the lead and the device. That can be reduced through the use of alligator clips that attach to the meter leads That does improve it, but it doesn't eliminate it. With 4-wire resistance methods, you have one circuit providing the current. It provides a known current. And even if there's a slight variation in the resistance of the connection for the current circuit compensates for that so that the current remains more or less fixed. So the current isn't an issue, and the voltage readback, here's where the 4-wire really gains its advantage. Because if you have a couple of tenths of an ohm dithering in your contact resistance, it's irrelevant because the meter's input impedance of about 10 mega ohms utterly swamps that noise, so you don't even notice it. That's really the secret of the 4-wire resistance accuracy, is that the high impedance of the voltage input negates most of the generally small dithering of contact resistance. That's a huge advantage. Okay, what we're going to do now is use the second method, where we use two multimeters, in this case the Benchtop for the voltage and a Fluke 85 for the current, and we'll provide the current with these bench power supplies. So we can apply the current, read the correct value through the current meter and the voltage from the bench meter, and then we can alter the current. So let's actually make a table and try different current levels and see what we get. So we're starting at this value here, and I'm showing approximately 51 microvolts and 1.23 milliamps. Now, getting it set more precisely than that is kind of difficult with a bench meter, like a bench power supply like this. So I'll go to 3 milliamps now, and I think I have to set that to 4 to actually get that. Yes, so setting it 4, I get 3. Go figure. Anyway, at this setting, I'm now reading 133 microvolts and 3.23 milliamps. Alright, now let's go up to, I think 11 milliamps will get me 10. Yeah. So at this current, I'm now showing 420, so 420 microvolts and 10.22 milliamp. Alright, next 31, I guess. Alright, so basically at an actual 30 milliamps, we're very close to that. I'm showing 1.229 millivolts and basically 30 milliamps. Next, 101. So there we are, right at basically 100 milliamps. So 4.093 millivolts and 99.9 milliamps. Okay, now 300. So I guess 301, I guess. 302. Okay. So now we're at 12.293. We'll make that 4. And 300.1 milliamps. Okay, next up, basically an amp. So we'll go like 1002 milliamps. And I have to change the range here. So basically 1000 milliamps. And I'm showing 41.00. Well, what's happening now is the voltage drop is continuing to increase, because at about 1 amp, and actually a little bit at 300 milliamps, I'm actually starting to heat the wire up a little bit. So the resistance measured is going to continue increasing as the wire warms up, because the wire has a positive temperature coefficient, and as it heats up, its resistance increases. So the voltage is continuing to increase. So we'll watch this until it stabilizes or slows down, and then we'll record the value. And then we'll do one more test point at 3 amps. So I'll pause it here and then restart once we've stabilized. Okay, I think we're pretty close to where it's going to top out at. So we'll make this 41.074 and 1000 milliamps. Now let's go to 3000. And now look at the voltage. It was 123.5, and then it's continuing to increase. The current hasn't changed here. The current's stable, but at 3 amps, now we're getting a more substantial heating effect. And remember, with a resistance circuit, the heating is I square R, so we've tripled the current, so the heating effect is increased by a factor of 9. So you can expect a more substantial increase in resistance as a consequence. And once we get this table built, I'll put it into an Excel spreadsheet and do a plot of that, and then we can take a look at that. Okay, we're getting pretty close to the top point of the voltage drop, so 125 point, we'll call it 450. 450 and 3000 milliamps exactly. Okay, so here's the graph of the data I entered in. So I have the voltage values, which are the voltage drops, and the current values that I set into it, and then calculated the resistances based on, V divided by I equals R. So anyway, those are the resistances all at those various current set points. Now this is the graph of that, like this. And you'll notice initially at just over a milliamp, it's up just under 41.5 milliohms, and then it drops down to a little under 41 milliohms, like 40.97. Thereabouts, 0.967, 0.97, 0.966. So that's the bottom value, and that's probably representative of what the actual resistance of this wire is. As you increase the current, however, beyond about 100-ish milliamps, so we're at, let's see, 1 milliamp, 3 milliamps, 10 milliamps, 30 milliamps, 100 milliamps, 300 milliamps. Okay, upwards of about 300 milliamps, we're okay, and then beyond that, that's when we're starting to get some heating. Remember, we're going from 300 milliamps here to 3,000 milliamps here, so a 10-fold increase in current, which actually results in a 100-fold increase in heating effect, I square R. So up to about 300 milliamps, the heating effect is pretty negligible, but at 1 amp we can see the resistance is curving up again, and then at 3 amps, 3000 milliamps, it has definitely climbed. Now that is, again, a consequence of the temperature coefficient of resistance. This guy I'd shown you a little while ago. So in addition to the errors that can occur owing to the Seebeck effect, which is most noticeable at very low resistances and low current. In addition to that, if you run with higher current, and it's going to vary depending on the circuit where that point is. But if you run with higher current, then you're going to begin to see the heating effect, which in this circuit looks to be something beyond 300 milliamps. Now there's a little bit of heating actually at 300 milliamps. There has to be. There's a little bit of heating at 1 milliamp. But again, with the I square R factor there, oops, with the I square R factor there, a change from here to here of 3,000 is like a 9 million to 1 change in heating effect. So just a huge difference. The I square R term definitely plays a role there. Now, relating to the Seebeck effect, however, I think we're seeing probably something of the Seebeck effect here, right? And as we increase the current, the voltage drop increases proportionately, and whatever Seebeck voltage offset we have is now a smaller percentage of the total, so that essentially the signal gets stronger and the noise gets weaker. Well, the noise stays the same, but the signal gets stronger, so the signal to noise ratio gets better. So, like I said, down around the 30 to 300 milliamp range is where we have probably our most accurate actual reading for the resistance of that circuit in the sub 41 milliohm range. And then beyond the 300 milliamp current value, we're getting a heating effect which is at that point your error is getting pretty substantial. And actually it looks to be at probably somewhere around about 2 amps, thereabouts. The effect of heating would be fairly comparable to the effect of what I'm presuming to be the Seebeck effect here. Okay, so we've set back up again with the 4-wire resistance setup using the bench multimeter in 4-wire mode. So just the one instrument. And at the moment it's reading 46, 47 milliohms. And if you recall, the accurate, I think the most accurate reading we have using the higher current and the 2-meter method showed a resistance right about just a little bit under 41 milliohms. It was seems to be the correct value. So looking at the 46, 47, are we seeing any thermal effects, any Seebeck effect? The way that the precision higher dollar bench multimeters with offset compensation work is they remove the current and then null out the voltage and then reapply the current. So we're showing 46, 47 milliohms. Let me unplug the current source. Now we're showing about 5 or 6 milliohms. Let me do a relative, which zeroes that out, plug it back in again, and whoa, 40, 41 milliohms, just as we got with the higher current value. So that seems to be the correct value. So what I just demonstrated is how you can manually accomplish offset compensation. I'll redo it. So let me remove the relative or the offset. I'm showing 46, 47 as the value, but I'm also seeing 5 or 6 as the offset. That's a measurement with no current flowing, so it's not real, it's not correct. So if I do a relative, which zeroes that out, then plug back in again, reapplying the current, I'm now measuring 40 to 41 milliohms. It's right at that point. And remember, what we calculated as the most likely best value was around about 40.9 milliohms. A little bit more than 40.9. So we're dithering right between 40 and 41, which probably is within a tenth of an ohm or so, a tenth of a milliohm or so of where we're at. Tenth of a milliohm, in other words, 100th of a 100 microohms. Anyway, let me take the relative out here for a second. So we're showing the well, let me put it back in again. Oh, I can't do that. Now do the relative. Okay, so that's the compensation for the Seebeck effect as it is now. But I can change the Seebeck effect by heating up a side. If I heat up the positive side, the measured resistance should go down. So watch. So it's going down. I'm adding to the effect or subtracting from the effect, depending on which direction it was initially. And if I use my hot air gun, and let me bring that out, you'll see that I can make a vastly greater change in the values beyond the 4 or 5 or 6 or so that I can do with my fingers in a short time. So we'll let that come back up to about 40, 41. I have my hot air gun. It's up around 175 degrees C. I'm not going to be holding it on there for any length of time. I don't want to burn anything up. So we're up right back to 40 milliohms or so. Now, just again, I showed this in my other video, but we'll duplicate it again. The mere presence of the iron does not change the resistance. It's not an electromechanical thing or the metal that's causing it, and either side. So that's not the effect. Watch what happens when I apply heat, though, from the hot air gun to the minus side. The resistance is going up, and going up by quite a bit. And if I apply heat to the positive side, the resistance goes down, and goes down by quite a bit. So the hot air gun is obviously able to apply more heat, greater temperature, than I can with my fingers. So the effect of the Seebeck effect is greater. Okay, so I'll let that come back to the point, and let me remove the relative. And let's see what the offset is showing. 4 or 5. That's different because there's a differential heating of the junctions, the connections. So I'm showing about 5. So the actual value should be about 41 milliohms. That's the closest whole number. 41 milliohms would be with a 0 offset. So if I was to bring up the resistance by heating up one of the joints, and then as it came down to say 51, I should see an offset of 10. So let's try that. Let me heat up. We'll get this so that it's going to take it a while, so it comes down slow. Okay. So I put that back, and now let's watch to see when we get to 51. If I unplug the current source, we should be right at about a 10 milliohm offset. Getting there. Getting there. All right, 51 and then 10. How about that? Right on the money. So we still have about a 10 milliohm offset, owing to the fact that the negative side is still warm. But even when we were kind of at an equilibrium there was an offset of, what was it, 5 or 6? So we were as if the negative junction were somewhat warmer. So, and it's hard to know ahead of time or what the rhyme and reason as to why you're getting the offset. But the point is, it's there, and pretending it isn't doesn't make it go away. So we'll let that stabilize just a little bit more. I'll unplug, do a relative, plug it back in, and right again to the 41 milliohms. So take the relative out. So that's offset compensation, and the way you can do it in a manual way versus the more expensive instruments that have that built in is to basically unplug the current. And on a meter like this, the current generally comes from the connection points where you normally connect up to the meter for doing volts, ohms, that kind of thing. And the voltage readback in 4-wire, it comes in on what they call the sense circuit. So the current is provided by the normal high-low connections, and the voltage readback for 4-wire is done in the sense high-low. Okay, in summary then, the three methods for doing 4-wire resistance measurements, the first one of which is using an instrument, a meter that has 4-wire resistance built into it. It's the simplest way of doing it because you just have the one instrument, the single DMM, but you do need two sets of meter leads, 4 leads altogether. One set of leads, 2 leads to provide the current to the device, and 2 leads, 1 set of leads to provide the readback of the voltage drop across it. But even with this setup, you still have issues of thermal effects, the Seebeck effect, that you can compensate for with by removing the one of the leads providing current to the unit, zeroing out the instrument, and then plugging it in. So that's the normal way of doing 4-wire. But the second way, and I think arguably potentially the most accurate way of doing it, is using 2 multimeters and a power supply. And the reason I argue it's more accurate is that you can use a different current value, not just the fixed 1 milliamp one that the 4-wire resistance circuit in the precision bench meter has. You can use a higher current, and up to a point, running with higher current has the effect of reducing any errors that are there through as offsets, either thermally or otherwise. So running at 100 milliamp versus, say, 1 milliamp reduces whatever effect by a factor of 100. And as you recall on the graph, the best values in what appeared to be the best values in the sub 41 milliohm range were at 30 milliamps, 100 milliamps, and 300 milliamps. So right around about 100 milliamps in that range. So I think for me, although it's a somewhat more cumbersome setup, and of course you need 3 items, 2 meters and a power supply, it has the opportunity of negating most of the negative aspects of the offset problem by simply swamping it with more signal. You do have the problem, however, if you go too high in current, of producing heating effects which increase the resistance. And of course you have to be sure that the circuit you're testing can handle whatever current you're putting into it. Now we're doing purely resistive circuits like resistors, for example. That's a fairly easy calculation. You know what kind of wattage you can handle. So calculating how much current against a resistance will give you whatever the wattage would be. The third mechanism or method for doing 4-wire resistance is perhaps simpler than the second one, because you only need the one digital multimeter, again in this case only operating in volts mode, but it has the limitation of relying on the current accuracy of the power supply. Now, some super high dollar power supplies would probably be perfectly adequate for that. But for a power supply like the Rigel DPA32 that I'm using, which is a decent, entry-level bench power supply, you're lucky if you see much better than about 1 milliamp accuracy. So if you're trying to set a 1 milliamp and you have a 1 milliamp or potentially greater error, then you're not going to be able to do very well. Going with a higher current, say 100 milliamps, a 1 milliamp error, is a 1% error, so less of an issue. Once again, running with a higher current gives you an opportunity to avoid some of the error aspects, but you do have the two concerns about running with higher current. Is it going to be tolerable for your circuit, for your system under test, for your resistor or whatever it is? You don't want to run it to it fails. Well, and the other factor is resistance heating, I2R heating, that results in usually an increase in resistance calculation. And then finally, on the increase in resistance, that is based on the temperature coefficient of resistance of the various device. And on a piece of wire, copper wire, the alpha is typically reported at that value, and obviously it could vary somewhat based on the alloys that they're using and whatever impurities might be in it. So that's the value, sort of a median value for copper, and it's likely to be somewhat different for one piece of wire versus another. But in any case, you can see that a change in temperature will result in a change in a change in resistance. Now, copper has a positive temperature coefficient. Some materials will have a negative temperature coefficient, so you will see a minus side in front for the alpha. So, I hope that was of some interest to you, and learning that you can use regular multimeters to do very precise very precise resistance measurements of even very, very small resistances should be of some value to. Okay, one last little bit, and this is actually something of a quiz. In the 2-meter setup where we varied the current, we saw that the minimum resistance value, because it started high, then went to a minimum, and then started climbing again as the current went up. The minimum we had was right around about 40.967 milliohms. And when we increased the current to 3,000 milliamps, the resistance went up to 41.817 milliohms. Let me write that down. So at 30 milliamp, R equals 40.967 milliohm. At 3,000 milliamp, R equals 41.817 milliohms. Question: what's delta T? You have everything on that sheet of paper to answer the question. So if anyone wants to pop that answer into the notes or into a reply, we'll see who gets there first. Thanks.